and welcome to Elements of Neural Networks and Deep Learning Part 1. This is the first part in a series of presentations on elements of neural network and deep learning, and my name is Tinyam V. Ganesh. This presentation and most of the subsequent presentations are based on material from two courses I had done on Coursera, namely Neural Networks and Deep Learning by Professor Andrew Ng at Coursera, and Neural Networks for Machine Learning by Professor Jeffrey Hinton, University of Toronto Coursera, and two books, Neural Networks and Deep Learning by Michael Nielsen, and Deep Learning book by Ian Goodfellow, Yoshua Bengio, and Aaron Corwell. I've also used other material from the internet. So let us look at why do we need deep learning. If you look at this set of handwritten digits, our brain is almost immediately able to recognize these digits as 5, 0, 4, 1, 9, and 2. If you were to write a computer program to be able to recognize any one of these digits, we would find it extremely difficult. So for example, if we try to write a program to be able to recognize this digit 5, we could write code which we could say that there is a horizontal line at the top, and then there is a small vertical line towards the side, and then there's a small loop at the bottom. But for different handwritten variations of the number 5, you would have to write different programs, and there would be so many edge cases and boundary cases that it would almost be impossible to write a program to be able to detect all the possible handwritten 5 and the number 5. Let us look at the picture on the bottom. These are all three pictures of cars in slightly different orientations. Again, if you try to write a program that could programmatically be able to identify a car from other images which are not cars, it would be almost impossible, because you can see each of these cars are at a different view and a different perspective, and we could never possibly write a program to take into account all these possibilities. And this is where deep learning comes into play. What is done in deep learning is we train our deep learning model or algorithm on 100,000 images of cars, and we let the algorithm actually decide what are the features it needs to be able to recognize images of cars, and then we test it out on a new data set which are cars, and it is able to correctly identify these. We will look in subsequent sessions at how this is actually done. But this is how deep learning, we train the model on a set of images, and then we let it learn all the key features it needs to be able to identify cars, and then subsequently use that for recognizing cars. And deep learning is basically inspired by the human brain, how the brain functions, though we still do not know how the brain functions, but with the known facts, the deep learning has been modeled. And here's an interesting quote by Professor Jeffrey Hinton, who says thought is a big vector of neural activity. Now let us look at the fundamental unit of our brain, which is the neuron. Basically on the left we have what is known as dendrites, which takes inputs from other neurons, and then we have a long slender body which is the axon, and at the other end of the axon we have the axon terminals. And these axon terminals are connected to other millions of other neurons through synapses. So here's a small example of what happens, assuming we have inputs at the ends of the dendrites, let's say x1, x2, x3, and based on these inputs, there is a potential gradient that develops across the length of the axon and causes an action potential to trigger on this neuron. And depending upon the inputs, this can either this action potential can either propagate to the network of neurons downstream, or it can inhibit the network of neurons downstream, and this action potential is carried across these synaptic connections to other neurons. And this is how information is transmitted and received across the network of neurons. So an average brain consists of about 100 billion neurons, and there are close to 100 trillion synaptic connections. So each neuron is connected to millions of other neurons through synaptic connections, and the neurons communicate through each other through these synaptic connections. The connections between the neurons are not static, but they keep changing. So if you continuously do some activity, you'll find the neural connections tend to get stronger, and if some thing is not we don't focus on something for a long period of time, then these connections tend to die away. And the interactions are not merely electrical, they are actually electrochemical. And the electrochemical signal released by the particular neurotransmitter may encourage subsequent cells to fire or inhibit other cells to fire. So the neural network and deep learning networks are essentially modeled, at least approximately, on how we think the brain functions. Neural networks have been around for a long time. In fact, they've been around since the 1950s. And when as the threshold neuron, Warren McCullough and Walter Pitts came up with this threshold neuron, and then Frank Rosenblatt in the late 1950s came up with what is known as the perceptrons. So he had written a book called The Principles of Neurodynamics, and he had invented the perceptron. So let us look at how the perceptron was used to learn some set of features. So how the perceptron learns is we compute a linear activation Zi as the weighted sum of the inputs plus bias. Here we have a set of binary inputs B1 binary inputs, and we have weights. So for a set of binary inputs xi, we give it weights and then plus a bias, and then we compute the linear activation. Now if this output Zi is above a threshold, then it is considered to be a 1. If it is below a threshold, it is considered to be a 0. And then this perceptron is trained on a given data set. If the output correctly classifies the data, then we not touch the weights. However, if the output classifies a 0 as a 1, then the learning procedure of the perceptron, basically we subtract from the feature the weight. And if the output incorrectly classifies a 1 as a 0, then we add the feature to the weight. So just doing the simple iterative procedure for every data set, we compute the set of weights, and then the perceptron learns and it can do some interesting stuff. So in the late 1950s, perceptrons was a big breakthrough and was supposed to be capable of many things, including the ability to walk, talk, see, write, and also reproduce itself. However, Marvin Minsky and Seymour Papert of MIT came up with a paper called the Perceptrons and proved that the perceptron was truly limited in its functionality. Specifically, they showed that when the perceptron was able to classify linearly separable data sets, it was not able to classify data set like, for example, the XOR function. So here's an example of an XOR function. So for example, the XOR is when the outputs are the same, when the inputs are the same, the output is 0, and when the inputs are different, the output is 1. So here's a simple data set. You can see that if we assume this region is a 0 and this region is a 1, and similarly this region is 0 and this region is a 1, then when you have a 0 0 or a 1 1, we have one data set, and when we have 0 1 or 1 0, we have another data set. And a perceptron was not able to come up with the non-linear boundary to be able to differentiate these two data sets, and that's where the shortcoming of the perceptron was actually shown to be somewhat lacking. So after this paper where it was shown that perceptrons were not actually as good as it appeared to be, there was a small slowdown in the neural networks. But then in the late 1980s, Jan LeCun came up with the handwriting recognition convolutional neural network, which was a major breakthrough. So here let us look at how this demo of Jan LeCun. So you can see as the handwritten digits come here, it is able to detect the digit over here. S- what is machine learning? There are two types of machine learning. One is known as the supervised machine learning, and the other one is unsupervised machine learning. So in supervised machine learning, the data set is labeled. So basically, we can consider it as we have a set of input features, and we have a corresponding output label, and we train the machine learning algorithm on this known data set. So we for every row in the data set, we have a corresponding output, and we train the machine learning model, and based on that it is able to learn. So for example, in supervised machine learning, we want to identify the price of a house based on features like the number of bedrooms, the location, and zip code and things like that. Then we have this click ads where on a web page we would like to identify the probability of being somebody being able to click the ad. And then here's another important machine learning, which is supervised machine learning, which is spam emails, to detect whether emails are spam or not spam based on the subject of the mail and the contents of the mail. Audio transcript, getting the transcript given the audio speech, image recognition, speech recognition, for example, your Siri or Alexa or Google Home, and then machine translation, so translation from one language to another. Unsupervised machine learning is when we use machine learning to detect patterns when the data is not labeled. Now, before I go into further, I would like to make a small digression into machine learning and show some of the main concepts of machine learning so that we understand, so that we can understand deep learning and neural networks much better. So machine learning, there are two types of machine learning. Basically, supervised machine learning, when the data set is labeled, there is for a set of input values or features, there is a known output value or target value. So, and unsupervised learning is basically when the data is not labeled. So in supervised learning, it's basically like the way we try to teach a baby. We show different pictures of apples, and we keep telling the baby that it's an apple. And similarly, by repeatedly doing this for apple or a bat or a ball over a period of time, the baby learns. Similarly, supervised learning is like that. So for example, let us take an example. Let us assume that the salary of a person is actually dependent on the age. So and we have a data set for different ages. We have the salary, and these are these black points. And this is a simple example of a linear regression where we have one input feature, basically the age, and we have the output variable or the target value, which is salary. So we want to know what is the relationship between this age and this salary. So we want to see how does the salary of the person vary with age, and can we represent this as a relationship as an estimated function f dash. Can we identify some function where we have f of age is salary? So we can assume that this is some weighted sum of the age plus some bias, and let's assume this is actually satisfies this data set which you can use. And how do we go about this? So we could try to take a line and fit this line over the points. Now this is a very bad fit. We see that doesn't pass through any of the points. Then we could try something like this. Again, it doesn't fit. Then we take this blue line. We see it does a decent job, but not that much of a good job. And lastly, we try to use this black line, and basically we see that it does a fairly good job, a representative job of actually passing through all the data points. But what are we actually doing when we are actually drawing different lines to these data sets? What we are actually trying to do is we are trying to find which line actually gives us the best fit. And how do we go about that? Is there a mathematical way where we can actually identify which is the best line that fits this? And the way that is done is, assume that this blue line is our estimated line, and these red and these points is the data set. And what we do is, from these data points, we draw perpendiculars to our estimated line, and we compute the distance between this data point and our estimated line, and take the square of the distance from this estimated line. We take the square because if we just take the absolute value of the distance from these points to this estimated line, then for lines for the points lying on opposite sides of the estimated line, it will cancel out. So we want to find the total distance of the points from an estimated line, and so we compute what is known as the mean square error. And how we compute the mean square error is what is the distance between the actual minus estimate the whole square. That is the actual data point versus our estimated data point, which is on this line. We compute the square of those distance and we take the mean of this distance, and if that mean square error is the lowest, then our line has the best fit. So for these different lines, we'll find the mean square error for this black line being the lowest, because if I drop perpendiculars from all these data points to this black line and take the square of the distance from the actual data point to the point on the data line, and we take the average, you'll find it is the lowest for this black line and very high for these higher lines. So that is what we need to do in a simple machine learning algorithm, which is linear regression. So here is another simple example to highlight what I was trying to say. Let us assume our data points are these points 1, 1, 2, 2 and 3, 3, and we need to find the best line that actually passes through these all these 3 points. So we could start with this yellow line, and as we know, the equation of a line which passes through the origin is W1x. So for different weights, we try to find the mean square error. So for example, if I choose W is equal to 3, then I get this yellow line, and again I find the distance from this estimated line to this actual point and take the square of that. And similarly for I keep doing it for different slopes. For this for W3, slope is equal to 3, slope is equal to 1, slope is equal to 0.5, slope is equal to 0, etc. So you can see that when slope is equal to 1, it actually passes through all the points, and the mean square error will be 0. And as the slope keeps decreasing, we get different points, and again the mean square error increases. So if you plot this, that is for the different values of the weights, we plot the mean square error, you will get a parabolic curve. And how we actually compute that the value of the weight which will result in the lowest mean square error, or the cost or the lowest mean square error, or the best fitting line is known as a technique known as gradient descent. So what we do in gradient descent is we cannot solve this equation, so we start at some arbitrary point on this curve, and at that point we find the slope. Slope is actually y2 minus y1 divided by x2 minus y1. So in this side of the curve, the slope will be positive. So, and then that is, the slope is dj divided by dw. Okay, for small change in the cost, what is the change in for small change in weight, what is the change in cost? This slope will be positive. So from this weight we subtract w minus alpha dj by dw. So since the slope is positive, so basically I am subtracting from w alpha into some small positive value, which will be a small positive number. So from w I am subtracting a small positive number. So essentially my new value of w will be slightly less than this, so I will move in this direction. Alternatively, if I had started from any point on this side of the curve, this side the slope would be negative, and if I do w minus alpha into dj by dw, now dj by dw is negative, so minus of alpha into dj by dw will be a positive number. Minus into minus will be plus, so I will be adding to this original weight w a positive number. So I will move in this direction. So whichever side of this curve I start from, I will eventually move towards the minimum, and I will finally reach the point where my cost or the mean square error will be lowest. And at that point where the cost is minimum is the set of weights which will satisfy this data set. So the essential goal of gradient descent is to identify the set of weights for your machine learning model which will give you the lowest cost. So here's a simple multivariate regression. So we have a set of input features x1 up to xn, and we have a corresponding output value or variable. It's also called the response, the target, or the dependent variables. These input values or input values or input features or independent variables or predictor variables are all called by different names. So essentially, your y value or a y predicted or y estimated is the weighted sum of these input variables, input features or independent variables. So this is what we need to find in multivariate regression. The other situation is when we do logistic regression, where we actually the output is actually one of two classes, class 1 or class 2. It is a binary value. So again, we try to see what is the relationship between these input features and the output variable or output response or the target. And we can use this, there's something called a sigma, which you'll see later. So what is the machine learning model? What are we still trying to do? We need to find, we want to have a function and which can be a weighted sum of the features, and we need a machine learning model to identify the weights of these weights for this equation, such that for every value in our data set, these weights will satisfy these outputs, and it will be as close to the output, and we will get the minimum error. And how is it usually done? In machine learning, assuming this is our data set, we can divide our data set into 70% training set, and we train our machine learning model, get the weights which result in the lowest cost, and then apply those weights on a new data set, which is a test set, and make sure that it performs well. There's another a more refined way, where we take 60% of the data as a training set, try out different models, find the best model, and then test out that model on a validation set, which is 20%. After we are sure that it does well, we test out the remaining 20%. So here are simple use cases of machine learning. So for example, we want to identify what is the miles per gallon given for when we have data set on different cars. Here these are all hypothetical, not real values, and we have the features or the variable input variables or independent variables as the number of cylinders in the car, the displacement, and the horsepower, and we have the corresponding miles per gallon. So given this data set, we can train a machine learning model that can learn these outputs. And in the cloud, let us assume that we have an e-commerce website where we receive a lot of traffic at different times of the day, different days of the week and months, and we have historical data on whether we needed to auto scale that our cloud platform or not. And we have historical data for this. In the month of September, on Friday at 6:30 p.m., the traffic was 150,000 hits per minute, and the CPU percentage usage was 70%. And we actually needed to add an extra VM, which was a medium-sized VM. Similarly, in March at 8:15 p.m., the traffic was 180,000, the CPU percentage was 91. We needed to add a large VM, etc., like that. So again, we can train a machine learning model to help us do this. Now let us go back to our deep learning. That was just a small diversion to give us a good idea of where we are going. So there are basically three types of neural networks. One is the feed-forward neural network, where we have a set of input features. We have a number of hidden layers and an output layer. So it goes in the forward direction. Then we have what is known as convolutional neural network, which is typically used in image recognition. So it has been used very successfully in not only being able to recognize images, it's also been able to recognize multiple objects in an image. So we take an image and then we apply multiple transforms to it, and then finally feed it into a deep learning network which classifies the images. And then we have what is known as recurrent neural network, which is used on data sets which have some sort of a time series. So for example, it is used mostly in natural language processing. So for us, in any language, we know that for example, in the English language, our spoken our speech or written text or anything, it's all it follows a sequence. So for example, we have the article, the or a followed by a noun, then we have the verb, then we have the adjective and things like that. So it is a sequence. So when you want to learn sequences, typically recurrent neural networks are used. Then we have generative adversarial neural networks, which was invented by Ian Goodfellow, and lastly capsule network, which was invented by Professor Geoffrey Hinton very recently, and a few of his other colleagues. So why is AI and deep learning taking off? In fact, the last decade there has been a tremendous progress in deep learning. One of the reasons is we now have much faster CPUs and much more advanced storage technologies. Secondly, we have tons and tons of data. There's exploding data from, we have mobile data, we have data from IoT, we have big data, retail from retail data, etc., etc. So that is one of the reasons why deep learning has been taken off. And but why does it perform so well? So if we try to plot the amount of data versus the performance in regular traditional machine learning algorithms like our multivariate regression or support vector machines or random forests, as the amount of data increases, we will see that it performs pretty well initially, but then after a point, even with increasing data, the performance actually plateaus. For small neural networks, the performance increase, but actually with more data, it actually shows a small appreciable increase. Medium networks, it again actually increases and increases linearly, and for large neural networks, there is almost a linear increase of the performance with increasing amount of data. But however, actually tuning large neural networks can be a bit of a trick, and it can take a long time to learn. But the fact is that they do tend to perform better and better with more increasing data. Now let us take an example of a simple neural network. Given a size of a house and a price, let us assume these are the data points. We can actually draw a simple straight line which will pass through all these points. And we also know that if the size of the house the size of the house which is less than this, the price cannot be negative. So we assume that if the size is less than this, the price is 0. And this can be actually we can use a simple use a rectified linear unit to fit the set of points, and this is a mathematical function which you can use to fit this set of points. That is, given a size, we can use a rectified linear unit neuron and actually predict the price. Now let us look at a neural network. So here we have what is known as the input layer, where we feed in our input features. So as I showed you the table, we have a set of input features or independent variables or input variables versus our output value or output target value or response. So we have a set of input features and we have an output layer, and in between we have what is known as the hidden layer. It is called the hidden layer because we do not know what it does. Okay, so and we can have as many hidden layers as we want in our neural network. If we have just one hidden layer, it is called a neural network. If we have more than one hidden layer, it is called a deep learning network. So this is basically the structure of a neural network. Now let us see how actually a neural network functions. Let us assume we are trying to estimate the price of a house given the size of the house, the number of bedrooms, the zip code of the house, and the wealth. So we can see that the size and the number of bedrooms are actually dependent on the family size of a different somebody with a larger family will probably want a bigger house with more number of bedrooms, and the zip code of the house where the house is located gives us a good idea of the proximity of the house to schools, colleges, hospitals, railway stations, and buses. Similarly, the zip code of the house and the wealth of the person will tell you something about the school quality. Now we can see that these new variables, the family size, the proximity, and the school quality, all have a bearing on the price of the house. So we can see how from the input features these relate to some other features which then subsequently determine the price of the house. However, when we are constructing a neural network, we do not actually tell the neural network which features actually have a bearing on which other feature and all that. We just input all the features to all the units in the all the different layers and let the neural network decide which features are important when it's trying to learn based on the input features and the output target variable. To illustrate this, how the neural network works, let us take a simple example. Let us assume that we are going to some fast food restaurant and we order 2 burgers, 4 packets of French fries, and 1 soft drinks. And the shopkeeper tells us the total price, which is 250 rupees, but he does not tell us the price of these individual items. So he tells us the total price is 250, and we buy these items. So how can we determine the price of these individual items, which are these which we can look at as the weight of our neural network? So the next time we go, we just order 1 burger, 2 packets of French fries, and 1 soft drink. And so based on our earlier experience, we assume a random price 20 rupees for each of these items. And if we had assumed 20 rupees, then it will be 20 plus 40 plus 20, which will be 80 rupees, would be our price. Whereas the actual price we saw here is the values in red, which is 50, 25, and 50. It is actually 150 rupees. So the shopkeeper tells we need to pay 150, whereas our estimated price is 80. So essentially we get a delta error of 70 rupees, and this error is also referred to as the cost, how well we actually did in our estimation. So in the next time we go again, we order a different set. We order 2 burgers, 2 fries, and 1 soft drink, and we now try to again change the price. We now assume it's a burger is 40 rupees, 2 French fries is fries are 30 rupees, 30 rupees, and a soft drink is 40 rupees. And with this assumed price, our estimated value would be 200, whereas given the actual price of 50, 25, and 50, it would have been 180. Now our delta error is 20. So again we are off. So we find that we cannot do this by trial and error. Now is there a way for us to be able to actually determine the weights of these neural networks, or the price in this case? So, and this is where neural networks come into picture. We actually use a technique known as gradient descent, which we have already seen in machine learning, where we have a complex a three-dimensional bowl. We start at any part of the bowl, and then we learn how to determine the combination of weights which will give us the closest estimated value to the real price. And we can see that if we change the weights by a small amount, the output value, the predicted value, also changes by a small delta amount, and the error also changes by a small delta error. So this we know, but the key question is, how do we change the weights so that it results in the lowest error or the lowest cost for all possible data in your trading example? So that is the key goal of our neural network. A neural network should be able to identify the set of weights for all the layers, which will result in the lowest error between the estimated value and our actual value, and that we will see how we can do in the next subsequent sessions. This is a quick example of a convolutional neural network used for image recognition. We can see that the intermediate layers seems to have learned some features. The next subsequent layer seems to have picked some combination of these features, and the other layer picks up these a more detailed example of the face. So the machine learning, the neural network itself determines what features to pick and what features to choose when we give it a given problem. We do not have to go about telling what features are important for it. So it learns by itself. And here's another interesting thing when deep learning meets art. Here this is done by a Google engineer, where the network has learned some art form, and then it applies it to real world images and generates certain sort of a surreal art. So here's another interesting picture of that. So the applications of deep learning are tremendous, and there is a lot of things that has been done from machine learning to language translation, image recognition, things like that, to almost composing music, coming up with all this, such strange art. Uh, so thank you. This ends the first session of deep learning and neural network part 1.